Welcome to week 3, I guess. Is it week 3 already? Week 4. Thank you. Time flies. So this week, we're going to talk about finite state machines all week, but I would need to finish up what we were talking about last week first. Last Thursday, it was combinational logic. So we're going to do that, and then we'll move on to finite state machines. So back to combinational logic from lecture 6. This was an example. I was presenting this as an example on how to use Carnot maps to minimize logic. And this was a BCD incrementer. BCD stands for binary coded decimal. It's a representation where we use 4 bits to represent one decimal digit. Right? So here are the decimal digits, and here's the corresponding representation. It's sort of the obvious one. Since we have 4 bits, there's some combinations of the 4 bits that are not used because we're only representing 10 things. So these are not used in this code. Okay. Now, the circuit over here, as shown here, is we'll take a 4-bit input, which would be a binary coded decimal digit, increment it by 1, and the output will come out here. All right. So I put the truth table for this function. If we increment 0, we get 1. If we increment 1, we get 2, etc., all the way down to here. If we increment 9, we get 0. It just wraps around. Okay. So the goal is to design a circuit, the combinational logic that's inside this box, to achieve this increment function. Now, this is the truth table, and there's actually 4 functions here. There's 1 function for each output, so we need to derive 4 different functions in order to implement the circuit here, because it has 4 outputs. Okay? So the interesting thing here is that we have these don't cares. In the truth table here, I put these dashes to correspond to where we don't care what this output function is. We're free to choose either a 0 or a 1 in these places, right? Because we can assume if this is a binary coded decimal incrementer, these will never appear as inputs. So we don't really care what the circuit does in those cases. So that's an extra degree of freedom that we can use. And using don't cares often helps us simplify the logic. Right? I'll show you how that happens here in a minute. Okay. So the function includes don't cares. So what we have to decide then is if we want to write. So what we're going to do is follow this procedure of Carnot maps that I presented the other day, and we can choose to do sum of products or product of sums. It doesn't really matter. I think in this case, sum of products will be a simpler expression. Okay. So I created 4 Carnot maps. 1 for each output variable. Remember, the outputs are W, X, Y, Z, if you look back here. Right? So we have 1 map for each column of the truth table. Right? And I filled them in with the values from the truth table. And you can just trust me that I did it correctly. I hope I did. And then from the truth table, from these Carnot maps, we can write down the 4 logic expressions that will represent the logic inside that incrementer. Right? So I put it over there on the board so I can actually go through the process since I don't have a stylus for my laptop. So we can go through the K-map process here. So you'll see another example on of how to use K-maps. So looking at W first, what we're going to do is capture all the 1s and cover all the 1s with the biggest groups as possible, where the dimensions of the groups are power of 2. Right? So we have 1, 1 here and 1, 1 here. We can group these 2 ones together like that. And then we've got a 1 here. We could group it. Remember, these tables wrap around. So we could group that 1 over here, or we could group it over here. But we might as well group in that 1 as well at the same time. See, these don't cares, we can use as 0 or 1. It doesn't matter. When we group a don't care with a 1, we're saying, well, we're going to treat that as a 1. Right? So this would be the way to do this optimally. So we have 2 groups, so we're going to have 2 terms. 1 term covers 4 ones, so therefore it's going to have 2 literals in it. This term covers 2 ones, so it should have 3 literals in it. So we can write that down. So W is going to be this one, which is CD B, and then or this term here, which is going to be D bar and A. Okay, so maybe you don't like the order of the literals, but that's what the function is. Okay, and then let me just do the others. X is over here. X has a bunch of ones, so this one, we can do a similar thing to what we did before. We can't bring that one in because that would make an odd size group, okay? But we can include this like that. So we have another group there, and they can overlap. We can reuse ones in multiple groups if we want, whatever we can do to make them big. And then this one here, will go like this. So I think that's the best we can do in that case. And I'll write this one down. So X is going to be CD B prime. And then this group here is C prime B. And then this one that wraps around is C prime D prime B. No? Did I make I have a feeling I got it wrong. Let's see. C D B prime, that one's right. This one is, oh no, this should only be, oh, sorry. Okay, D is constant 0, so it's D prime, and then B like that. Okay. I'll just circle the rest so you can see. I won't write down the expressions. Okay, so here we have 2 ones. There's not much, I think. Oh, this one we can get like that, right? And this one is like that, I think. And then over here, ooh, oh, this is nice. This is a big group. And that gets everything. So Z is just, what's that make Z? Anybody know? D bar, yeah. We might as well do this one while we're at it. So this is C prime D, A prime, or this big group here, B and A and B all change over there. So the only constants are C and D bar. Okay, so we got the logic expressions. We're pretty confident they're minimal. Then you could just, if you had logic gates, you could put together some logic gates to implement these equations, and you'd have your circuit. So there you have it. So not much thinking. It's kind of a mechanical process, and now you could design this kind of circuit. Any questions on this example, or Carnot maps in general? Okay. So I just wanted to show you this. So if we have more than, so these Carnot maps, these will do functions of 4 variables, right? We have 2 dimensions here, 2 variables per dimension. If we need to go to higher dimensions, if you have 5 variables, you can do this. You stack 2 of these 2-dimensional maps on top of one another, where this is the A equals 1 map, and this is the A equals 0 map. Right? And then you look for groups that are 3-dimensional groups in the plane and going up and down. If you want to go to 6 variables, you stack 4 of these together, where you have AB is the dimension moving this way, and AB goes 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0. Right? Again, this is a gray code. And again, you can group X and Y and then Z. Right? And remember, this top one is adjacent to the bottom one. In practice, I mean, people do this. I've used these. They're kind of awkward. We probably won't ask you to do one of these, but you should see that it's possible. If you need to go to more variables, then Carnot maps kind of run out of steam because you would need another dimension to do it. You'd need 4 dimensions. It's hard to think about that. Yeah.
Is this the technique that synthesizers would use?
Not directly. They do use the same theorem, the unifying theorem, but they apply it in kind of a more. We'll talk about it later in the semester, but they don't exactly use Carnot maps, but it's equivalent in some ways to what they do.
Can't you just add more rows and columns to the order?
No, because then they won't be add more rows. No, because
And just use a greater too.
oh, add another variable there. You lose the you lose the adjacency property. This is a flattening of a n cube into, in this case, a 3-dimensional cube into 2 space. Things that are adjacent logically won't appear adjacent on that kind of map, I think is what happens. So it doesn't work, but I don't know if I have a good way to explain it, but I'll think about it more later. Okay, so that was K-maps. Everything we've talked about so far is 2-level logic, right? This came up the other day. It's all ands of ors or ors of ands. Right? Now, sometimes you can do better if you're willing to implement multi-level logic, which actually we are often, and it comes up a lot. So here's an example just to kind of motivate this. Here's a function x. It's in reduced sum of products form here. And so it would have this implementation where it would have a bunch of AND gates feeding their outputs to an OR gate, right? They've got an AND gate for each term, min term there, or each term there. Now, its implementation in 2-level gates is the cost. We can look at the cost of this, and it's going to be 7 OR gates and 6 3-input. 1 7-input OR and 6 3-input ANDs, right? And by the metric I told you the other day, where we're about 2 transistors per literal, we end up with about 50 transistors. The delay through this, if you want to know what the delay, it would be basically the delay of the this is backwards. It would be the delay of this 3-input AND gate in series with the delay of that 7-input OR gate, right? So all the signals would have to propagate from here to here, so that would tell us what our delay is. Now, we'll see what that really means later in the semester when we look at the delay of gates. Now, we could factor this so that now in this new factored form, we have products. We have sum of products of sums. So it's 3 levels of logic, right? And I didn't really show you how I got from here to here, because it's kind of hard to do that. But if you multiply this out, it's use some kind of factoring, right? And if I multiply this out, you can see we actually get that up there. So this implementation would look more like this, where we have these 3-input ORs to implement these terms. Those get ANDed together, and then we AND in G here, or OR in G here. Right? So if you count up all the transistors here, this is more like 20 transistors. So it's actually significantly simpler and smaller than this implementation up here. And it's because we went to an extra level of logic, we were able to, there's some redundancy here effectively that you're able to factor out, right? And factoring is the kind of the common technique that's used to build, to generate multi-level logic from 2-level logic. And it's one of the heuristics that the tools use in order to simplify your logic. It looks for places to do factoring. Oh, and by the way, somebody asked the other day about the complexity of Boolean simplification, and I looked it up, and these problems are all NP complete. The 2-level simplification is, and multi-level logic simplification is NP complete at least. Very hard. And so the programs that do this use heuristic algorithms. So that means you probably get different results depending on which program you run. Okay, so that shows you multi-level logic. We're really not going to do a lot of problems like this because the tools do it for you automatically, but it's fun to do the two-level logic ones, but the multi-level logic gets more complicated. Which is faster? This is clearly simpler. It would take less chip area, the factored form. Here, we'll get into this more later. This looks like 2 levels. You would think this might be faster because you're only going through 2 levels of logic. Here you're going through 3 levels of logic from input to output. But these high input gates tend to be pretty slow, as we'll see later. So it's not really clear in this case which one's going to be faster. Using multiple levels will reduce the cost almost always. Sometimes it even reduces the delay because it simplifies things enough. Right? Sometimes there's a trade-off between cost and delay. So we do it mainly to simplify. So if you're mapping this to LUTs, then you'd need fewer LUTs possibly to implement a simplified version than the 2-level version. Let me show you another example of multi-level logic. Here it's this is another function here. In this case, we factored out things this way. We say let x equals ab and let y equals c plus d. Then you can rewrite that function as xy plus x prime y prime. Right? So we're using the x that gets computed, using it 2 different places in the circuit. Same thing for the y. Right? So we kind of factor out a sub-expression and use that multiple places. Right? So that really saves a lot. Right? And this is another thing that tools will look for is common sub-expressions that can be used multiple places. Right? So as I say here, no convenient hand method exists for multi-level logic simplification. So we're really not going to use it much here. But the tools that you use for your Verilog logic synthesis use algorithms and heuristics. And as I say, these are NP complete. As humans, we will implement multi-level logic circuits, but we'll do it in the cases where the structure is obvious. Like in the case of that ripple adder, for instance, that was, if you look at that complete circuit, the function that represents the last bit or the second to the last bit or the carry out, that's all implemented. By the time you instantiate those full adder cells, if you looked at the logic gates that implement that full, that 4-bit adder, that's a multi-level logic circuit. Right? And we are able to build it because we know the structure of addition. So often we exploit what we know about the structure of some computation to do the factoring. In that case, we factored that into column 1-bit adders and then cascaded them together. Right. Okay, so that's all I'm going to say about multi-level combinational logic. I wanted to say something about NANDs and NORs because they're important for CMOS because NAND gates and NOR gates are simpler to implement than AND gates and OR gates, as we will see later. So our understanding of NANDs and NORs comes from De Morgan's law, which we looked at the other day. And the way I remember it is if you have a bubble at the output of a gate, that means that gate is the output is inverted. So here's an OR gate with a bubble here. That makes it a NOR gate. If we want to move that bubble through the gate, we can do that. But when we move it through, it pops out at the 2 inputs, and it changes the gate from one form to another. It changes it from an OR to an AND. Okay? That's essentially that's a graphical understanding of De Morgan's law. It's the same thing. Same thing here. If you have these, and you also need to know that 2 bubbles in series cancel each out. That's a double inversion. If you invert something twice in Boolean logic, you get the signal back. Right? So we can do the same thing here. We can move this bubble through. It cancels out those 2 input bubbles and changes that from an AND to an OR. Right? So we've got 4 different combinations of those types of transformations that we can do. Now, we can use this idea of pushing bubbles around as a way to convert a circuit from ands and ors to nands or nors. Right? And a very common one is this and or circuit. It's very common because this is the generic form of a sum of products implementation of a logic function. Right? Sum of products, the or and gates are the products, and the or gate is the sum. So anything that we do using Carnot maps where we write down like these forms, sum of products, are going to basically look like this kind of thing where you have the or of a bunch of ands. Now, as I said, if you were going to implement this with transistors, you probably wouldn't use ands and ors because an AND gate is 6 transistors in CMOS, and a NAND gate is only 4 transistors. So we like to convert everything to NANDs. Right, so here's the little procedure on how to do that. Once you know it, you can just skip all the intermediate steps, but just so you can see how it works, what we do here is introduce bubbles. Yeah, we introduced bubbles everywhere. So I put I don't like this. Why don't I like this? I know it's the result is right, but oh, we know this. Okay, yeah. So I showed this on the other side. So an and here, we're going to use this one. This one down here. So an AND gate is like an OR gate with inverted inputs and inverted outputs. Right? That's because if we move this bubble through, it's going to change this OR to an AND. So we can replace our ANDs with these things. And then likewise, we can replace that OR with this thing, which is AND with inverted inputs and outputs. These two bubbles here cancel out because they're on the same signal line. So those go away. So we're left with this down here in C. And then we can move these bubbles through to the output. We get a single bubble at the output here, and that changes that into an AND type symbol. So we have NAND, NAND. Okay. So the thing to remember is AND or circuits can be implemented as NAND, NAND, which is kind of nice, right? Because if all you have is an AND gate, that's really all you need. You can do all your sum of products things with just NAND, NAND. Right. And I'll leave the other ones for homework. Well, okay, I could tell you this. By symmetry then, or AND, which is product of sums, yeah, product of sums, is going to be NOR, NOR. Right. Now, as we will see later, NOR is not as nice in CMOS as NAND is traditionally. It's getting better all the time, but it's not as good as NAND. NAND is, for the area, it's the strongest gate for a given amount of area. Okay, and then we could do a similar, so that was kind of a generic transformation here, and or we see those circuits all the time. Now you can just remember that's NAND, NAND. You might be presented with some multi-level circuit, and you'd like to implement this as NAND gate. So you have to kind of do this procedure yourself. You can introduce bubbles everywhere and kind of push them around, and you end up with NAND. So I'm not going to take the time to do this now, but maybe we'll have one on the homework so you get some practice doing this. All right. But if you kind of use this, what I just did here as a guide, you could figure out how to do this kind of circuit. And sometimes you may end up with an inverted input, or you need to have an extra inverter around. Right. All right. Last thing on combinational logic for now is I wanted to talk about exclusive OR, because exclusive OR comes up. It's already come up when we were talking about adders. It'll come up later in the semester when we talk about other circuits. It's an important function, exclusive OR. And so, we like to look at different ways to implement exclusive OR. Here's the function again. We also have exclusive NOR, which is the inverted version of exclusive OR. But exclusive OR is a one if and only if one of the inputs is a 1, but not both. So here it is. This is a nice symmetric function. We can write down, usually, often we, in case you haven't seen it, we use that symbol plus with a circle around it. So it's plus like OR, but it's exclusive OR. The only difference between exclusive OR is that we exclude this case, the 1, 1 case in exclusive OR. We don't exclude it for OR. It's a parity function. If you take the exclusive OR of 2 signals or 2 bits, it'll tell you the parity of those. It's also addition mod 2. It's a way to add 2 bits together and then take the mod 2 of it. It's the same thing. Here it is written out in algebraic form, as we saw the first day of class, I think, x prime y plus xy prime, which means you can implement it as a sum of products here. But of course, we prefer the NANDs. So here's the NAND version of exclusive OR. It's got, those are the derived directly from over here. And we added the inverters there to provide x prime and y prime when needed. And then there's this version of it, which I can't explain other than tell you that it actually is right. This was the homework problem. We asked you what this function was. And you should have been able to figure it out, so you probably proved to yourself at this point. So it's kind of a tricky version of this. It looks like this function back here, but then it has this extra NAND gate here, which serves the purpose of those 2 inverters. It's not actually fewer transistors than this. It's the same number of transistors, but I think it looks cool. It has a nice symmetry to it. So another approach is, if you look at, interesting thing about exclusive OR is that you can implement it with a multiplexer this way. If x is 0, then output y, otherwise y bar. If you look at this function here, if x is 0, then the output is y. If x is 1, the output is y bar. So it's like a conditional inverter. It inverts this signal x based on the value of, the signal y based on the value of x. So that's another way to think about exclusive OR. So it's a really fascinating function, and it pops up all the time, and it has lots of different implementations. And we'll look at more of them later, I think, when we look at transistor level circuits, but just thought I'd give you this now. All right, so that's it for combinational logic for now. And anybody have questions about any of this? All right. So we're going to move on to talk about finite state machines. Have people studied finite state machines in other classes?
They're in 61C.
61C. Oh, really?
Mm-hmm.
In the logic part of the course, right?
I think so.
Okay. Sometimes programming course, it gets introduced in programming courses too, but only in 61C.
That's only where I've seen it.
Oh, okay. Because it gets used in language processing. It gets used in lots of different places. Okay, so we talk about finite state machines in this class because it's a way to model the behavior of any sequential circuit. Right? In fact, everything we build with digital logic is a sequential circuit. So we could describe the behavior of any sequential circuit describe it as a finite state machine. Right? We typically don't, because it would make for a really big, complicated finite state machine, and it doesn't really buy us much to think about it that way. But we do use finite state machines as a representation for doing designs. Okay, if we are trying to design a circuit, if we can express it as a finite state machine, then there's an easy way to turn that into a circuit, either using Verilog or using hand methods, and I'm going to show you both of those. Okay, so that's why we study it. It's another kind of, it's a representation that we can use that help us think about sequential circuits and help us automatically do design. So, as with all sequential circuits, the output depends on the present and the past inputs, right? So the effect of the past inputs is represented by the current state. So the idea of a state machine is that It's in a state, an input comes, it might change to a new state, and it might change the output to a new value. Right? So this type of behavior is represented with a state transition diagram. And this is the essential part of a finite state machine. It's a thing that can be described with a state transition diagram, where we have a bunch of bubbles, and the state is of the machine is in one of these states at any one point in time, and only one of those states, right, for finite state machines. And then when an input value comes, we can move from one state to another. Sometimes an input comes and we just stay in the same state. So sometimes we'll move to another state, and another input, we might move to another state. And in this example here, there's outputs associated with the states. So when you change to a different state, the output will change to reflect the output that's associated with that particular state. Every state would have a unique output pattern. Right? In digital circuits, we build things so that there's we traverse one edge per clock cycle. Right? So this action of moving from state to state is moving synchronously with the clock. So as the clock comes, on every clock edge, we have the opportunity to either stay in the same state or move to a different state. And so the inputs are coming in synchronously with the clock, and then the state changes are happening with the clock. Okay. So this is kind of a powerful notion. We can represent lots of different types of circuits this way. Right? But I'll show you some simple examples so you get the idea. The implementation of these circuits kind of looks like this. So if we have this type of state diagram, right, what do we need to do? We need to have some way to represent which state the machine is in. Okay? So we have some flip-flops, a register here, which we use to hold the present state of the machine. And I labeled it present state here. And then we have some combinational logic here that takes the current input and the value of the present state that we're in, and does a little calculation and calculates what the next state should be to accurately reflect the behavior that we've specified in the state transition diagram. Right. Likewise, we have another combinational logic circuit here, which is a map from state to output. So for each state, we have a circuit here that figures out what the output should be for that particular output. And this is combinational logic too. Right? So these pieces, we should be able to design these using the techniques that we looked at last week and part of today, using kernel maps, for instance, if we can specify those functions. These are just Boolean functions. And then this part is just a register, which we can instantiate to hold the state. So it should be relatively, once we have this diagram, it should be relatively straightforward to figure out how to implement this circuit that behaves according to this state transition diagram. So we use flip-flops for the state register. Obviously, we have to figure out how many flip-flops to use there, how big that register has to be, and that has to do with how many states. It's going to be the ceiling of the log base 2 of the number of states tells us how many flip-flops. In other words, if we have n flip-flops here, we can represent 2 to the n different states. Right? So if you have a state machine with 6 different bubbles, 6 different states, then we need at least 3 flip-flops to represent that. We're not going to use all 8 combinations of 3 flip-flops, right? So we'll have some don't cares in these functions again, right? So we could use that to our advantage. Okay, I think I said all that. So we're going to learn how to implement finite state machines in Verilog. It's actually quite convenient. It's one thing that Verilog does really well. It lets us express finite state machines because we can use behavior, and we can use case statement to represent all the behavior of this state transition diagram. But first, we're going to learn how to design by hand at the gate level, just because it's fun and you should know what the tools are doing for you. So let's start with an example finite state machine. This is probably the simplest one you could ever imagine. It's a parity checker circuit. So here, I'm going to set up the problem on this slide here. we have a string of bits. We can say that a string of bits has even parity if the number of ones in the string is even, and it has odd parity if the number of ones in the string is odd. Okay. So we're going to design a circuit that takes an infinite serial stream of bits and outputs a 0 if the parity thus far is even, and outputs a 1 if the parity is odd. Right? So it will be changing its output according to how many ones it has seen. Right? So here's an example string. Time is moving to the right. We put in a 0, and then a 0, then a 1, then a 1, then a 1. If we put in a 0, the parity is, we're going to start out with even parity. Put in a 0, it doesn't change the parity. Another 0 doesn't change the parity. Put in a 1, now we have odd parity. Put in a 1, now we have an even parity. Put in a 1, odd. Put in a 0, it stays at odd. Put in a, okay, you get the idea. This is what the waveform looks like. Here's the clock signal. The inputs are coming. We can look at the on each clock edge, this positive edge triggered circuits as usual. That's the first 0 coming in, that's the second 0 coming in, that's the first 1 coming in. At that point, we change the output from 0 to 1 because we're reflecting the fact that the output now is going from even parity to odd parity. And it happens a little delay after that edge. Right? And then you can see that here's when it goes back to odd parity and then back to even. Okay? So how would we design a circuit that does this? You would guess that there's an exclusive OR gate in here, given what I just told you about exclusive OR being a parity function. But it's more than just exclusive OR gate because we have to remember the state, right? Because a 0 doesn't always give you the same output. If you're in the even state, a 0 gives you a 0 output. If you're in the odd state, a 0 gives you a 1 output. So the output behavior is dependent on which state you're in, right? So it kind of remembers somehow what state it's in. So that's what, so how are we going to do it? Now you could guess a circuit that would do this. You want to guess a circuit?
You could have like a 1-bit register where the input is or like what's like the D, like what's loaded in the next clock cycle is the XOR of the input bit string with the previous or the current value of the register.
So this is in, and you want to feed this back is what you said, right? And that's the output. This is D, that's the Q.
Or you could just have it sum, and since it's a 1-bit number, it'll just like overflow and be 0 if it's already.
Oh, do sum, yeah. Well, a sum is if you look at how to sum adding bits together, it's just XORing them. So it's the same thing. Like I said, this is addition mod 2. So yeah, so it's a really good guess. So let's see if we can get to this without thinking. So too much. All right, so we're going to draw a state transition diagram first. So here's the state transition diagram. If you're in the even state, the output is 0. If you're in the odd state, the output is a 1. Right? If you're in the even state and the input is equal to 1, you stay in the even state. If you're in the even state and the input is equal to 1, you move to the odd state. If you're in the odd state and the input is 0, you stay in the odd state. And if you're in the odd state, the input is 1, you go to the even state. So you just flip back and forth depending on what the input is, and you change the output accordingly. So circuit is in one of two states, transition on each cycle with each new input over exactly one edge. Output depends on which state we're in. Okay, so now how do we take this and turn this into a circuit? First thing we do is turn that into a table. Right? So here's a state transition table, which is a tabular version of this diagram here. I've enumerated everything. All the same information that's in this graph is in this table. Enumerate the different present states and input combinations, right? So what we need to look at is every arc that leaves even. There's 2 arcs leaving even, so we have 2 rows associated with even, and we have 2 rows associated with odd. So if we're in even, and we input is 0, we stay in even. If we're in even, the input is 1, we go to odd, etc. This column here just says what the outputs are. And that's just, in this example, it's just dependent on which state we're in. All right. Once we have that in that tabular form, we need to invent a code to represent the states. All right, and this is where we have some choice. And our choice of code will have some effect on the simplicity of the circuit. And we'll talk more next time about optimal ways to think about choosing codes. But for now, let's just say, let's let the even state be encoded by a 0 in the register, and the odd state be encoded by a 1 in the register. Okay. That's a nice way to encode it, as you will see in a minute. It simplifies some things. Now we can go and replace these symbols. We had done it symbolically. We can replace the symbols by their codes. So we replace all the evens with 0s and all the odds with 1s. And we get this thing that looks kind of like a truth table, where we have the ability to figure out what the combinational logic blocks are. Remember, there's 2 combinational logic blocks in my implementation. One is the output function based on the current state, and one is the next state function based on the current state and the input. So in this case, it's pretty simple. You look at present state and input, and the function is next state here. So 0, 0 goes to 0, 0, 1 goes to 1, 1, 0 goes to 1, 1, 1 goes to 0. Oh, look at that. This is exclusive OR function, and there it is. The next state is present state exclusive OR in. And then out, in this case, because of the code that we chose, is just out is equal to present state. You can see the out function here. It matches the present state exactly. Okay. If we chose to represent even in the flip-flops with a 1 and odd with a 0, the state machine would still function. It's just the output function would be the complement of present state. And I think it might change this to exclusive NOR. I'm not sure. But OK. So there's my really simplest possible finite state machine design. But this procedure I went through works for any finite state machine, really. OK. So here, then, given those equations, we can implement this and yeah, it's the same as I had on the board over there. OK. So the combinational logic circuits in this case are exceedingly simple, but I think you get the idea. So this is the process we went through, and I wrote it all out here because we're going to follow the same process for some other examples. You specify the circuit function that comes to you, or you specify it in English. You draw a state transition diagram based on that. Sometimes that's the hardest part. Based on that, you can write a symbolic state transition table. Then write down an encoded state transition table. Okay. From that looks like truth table. You can derive logic equations either by inspection, as we did in this case, or by using Carnot maps or some other method. You could write canonical forms and use Boolean simplification if you wanted to. And then you can derive a circuit diagram based on those logic equations. You add in a register to hold the state, and then you have combinational logic for the next state and for the outputs. All right? So I'm going to show you a bigger example that's a little more exciting, a little more fun. Okay. So here's an example of a kind of a baby combination lock. Okay. So this is a circuit here in the finite state machine here. It's going to have 2 outputs. One is called open and one is called error. It has some switches here that we can switch in order to enter in a combination. And then it has a couple buttons that we can use to help enter the combination. So the way this thing works, it's a not very secure lock, but it's a lock nonetheless. There's a 2-bit serial combination. There's 2 2-bit numbers that represent the combination. For example, the combination might be 0, 1, 1, 1. So what you do is you set the switches to 0, 1, press enter, then set the switches to 1, 1, press enter, and then open. This signal is asserted. So you can imagine that signal controls the solenoid that opens the bolt on the door, and then you can walk in. right? If the wrong code is entered after the second entry, then the error signal is inserted instead of open. Open remains 0, so the door doesn't open, and this just sounds the alarm and calls the police or turns on the LED or whatever it does. Okay? And then you could reset at any time and try again. Okay, so I think you understand the way that it works. Sounds like a fairly complicated circuit in there, but viewing this as a finite state machine gives us a very systematic way to design the logic in here. So the first step is to come up with a state transition diagram. And to save time, I'm just going to show you what it is. Here it is, and I can explain it. It's actually pretty simple, and I'm sure you could derive this yourself if you had a few minutes. So we have a start state, and that represents when the lock is just sitting there waiting for somebody to come up to it. And in fact, when we reset from anywhere, any other state, we just all go back to the start state. This would be the state when you turn the lock on, the power, put the battery in the lock, put the power on, we would probably build it so it automatically reset into this state. So it's ready, waiting to go. Okay, now, as long as, now enter is not, so I say enter bar here, this means enter is equal to 0. As long as enter is not pressed, we just stay in this state. So the clock is going, so we have to make a decision on what to do on every clock cycle. The clock's going, but as long as enter is 0, nothing happens. We're going to assume here that when the enter button is pressed, it generates a pulse that lasts for only one clock cycle. Right? Because when you press a button, there's probably 100,000 cycles that go by before you lift that button up. So we don't want this thing zipping through a bunch of states. We want just this very orderly one state transition per button press. Right? So we can build a circuit that looks at the button being pressed and generates a single pulse for one clock cycle on a button press. Right? And you'll probably do that in the lab if you haven't done it already at some point. Okay, so remember that. Okay, so if enter is pressed and we have a correct code in, all right, then we'll go to the state OK1. That's our way of saying we put in one good combination. If we press enter and a bad code is pressed, then we go over to bad one. We don't assert error yet, because that would tip off the user that they're on a wrong path. Well, you have to wait till they put in the second number, right? Okay, but we have to remember the fact we're on a bad path. If we're in OK1, and again, we just loop here, waiting for the button press. The button press comes with a correct code, then we go into OK2, assert open, right? And as long as we don't reset, we just stay there with the door open, and then at some point we reset and we go back. If we got the first combination number right, but the second one wrong, then we're going to come over here to bad 2. If we got the first one wrong, regardless, independent of the input, we'll just go into bad 2. I think that covers all the states. And then we can reset at any time back to start. Okay, people understand the state transition diagram? Okay, so that's the hardest part, actually. Once we have that, then we can make a symbolic state transition diagram. Now, what I assumed in that was that we have a little decoder logic here. And what the decoder logic does is it encodes our combination. So this is the circuit that we need to encode the two different combination numbers, 0, 1, and 1, 1. If the left switch is 0 and the right switch is a 1, then combination 1 will be asserted. If it's a 1, 1, combination 2 will be asserted. Right? So this is looking for these patterns, right, and decoding it on these two outputs. If you wanted to have a different combination, you just have a little bit different circuit here. You'd probably just move the inverter somewhere and or maybe put another inverter or whatever if you wanted to have 0, 0. Right. But this simplifies our circuit to kind of decouple the decoding of the combination from the, it kind of factors that out. All right, so that's COM1 and COM2. Those are inputs then to the circuit, along with the reset signal, enter signal, right? And then we have the present state representation here. And then these are the output things. We have open, error, and the next state. Right? And we're going to remember we're going to use this table to specify what the logic is. I use stars here as wildcards. Right? This table is actually really big because we have all these present states plus all the combinations, all of the zeros and ones for reset, enter, and COM1 and COM2. So this is just kind of abbreviated form. For instance, we look at reset. If reset is 1, and for all the other values of enter, COM1, COM2, and present states, the next state is going to be start. And the output's going to be 0, and the error is going to be 0. We can do this for the other ones as well. For like this one, for instance, if reset is 0, enter is 1, it doesn't matter what COM1 and COM2 were. For all those combinations, if present state is bad 1, then the next state's going to be bad 2. Right. So this just encodes that state transition diagram with stars meaning wildcards. OK, so what can we do with it at this point? Well, it looks pretty complicated, but we can simplify it a bit. For one thing we can do is this reset doesn't have to be part of the circuit. Resets, remember the flip-flops are registers that we have. Most of them oftentimes have a reset signal. So we can use that reset signal to reset the state to some known state. So that's one thing we use. If you do that, we end up with an encoded, OK, and then the other thing I did is assign states. So in this case, we have 1, 2, 3, 4, 5 states, so we need at least 3 bits to represent these 5 states. I don't know if I did an optimal state assignment. We have freedom. It's nice to have the start state be all zeros because it's natural to reset registers to all zeros, but it doesn't have to be. As you see, the registers that we provided you, you can reset to any value that you want. But I often use start as 0. OK1 is this one, OK2 is here. OK, so I just chose bit patterns to represent the different states. OK, once I have those and taking out the reset, this is a full specification of the encoded state machine where we have enter, COM1, COM2, present state 2, present state 1, present state 3. Right? Remember, we have 5 states, so we're going to need 3 flip-flops, so we have 3 bits that represent the present state. Right? And then we're going to have 3 bits that represent the next state here. Right? So that's like the output of this function, 3 functions, NS0, NS1, and NS2. I didn't put the output functions open and error in here, but they're pretty simple functions. Once we have this, if we wanted to use a Carnot map, and I'm not going to go through it for you, we could because we would have 3 Carnot maps, 1 for each of the 3 next state bits, and we have 1, 2, 3, 4, 5, 6 inputs. So it just works with 6 variable Carnot maps. So it look like we could set it up with this, where we'd replace A, B, C, D, E, F with enter, COM1, COM2, PS2, PS1, and PS0. OK, so that's another big example. And you can see the rest is just kind of mechanically going through, figuring out the logic equations and figuring out the right circuits to implement this. We used to build this in the lab every semester in the FPGA lab, but we've moved away from it. Questions on the combinational lock example? Yep.
Why can't you just the enter as a clock signal?
Why can't you use enter as a clock signal? Well, you could. Functionally, it would work. In practice, it's a little bit dangerous to build circuits like that. We tend to avoid that type of circuit because it's susceptible to noise and glitches. And
So switches or push buttons are
could be, yeah.
generate a lot of noise for a circuit.
If they did, you would get strange behavior. Switches do and buttons do bounce. If you look at the waveform coming out of the switch, it is kind of a noisy thing. So you'd have to clean it up somehow. The easiest way to clean it up is with a clock signal. So, yeah. So yeah, to answer your question, buttons and switches are pretty noisy. If you look at you don't get a nice clean transition. You get kind of a bouncy, noisy thing. So, okay. So now, another concept related to finite state machines has to do with the Moore versus Mealy, and I'll show you what that means. So all our examples so far have looked like this, where the output is based only on the present state. Right? Had circuits that look like this, where we have one combinational logic block that's used for going from input and present state to next state. And then we have another combinational logic block that's a map from the current state to the output. And this kind of matches this way we draw the state transition diagram, where we put the output values in the bubbles associated with the state. Now, there's another way to build finite state machines with digital logic, and it's where we associate the outputs with the edges rather than with the bubbles or with the states. Right? Here, the output function includes the present state and the input. Right? So the circuit looks more like this, where we have a piece of combinational logic where it has two separate outputs. It has the next state output and it has the circuit output. And both of those are a function of inputs and present state. So, all right, okay, so that's the difference. Remember, you can think about it as the output is connected, or is associated with the transitions in this type of machine, and we call this a Mealy machine after, I don't know, somebody named Mealy. And this one's called a Moore machine. And in the Moore machine, the outputs are associated with the states. So I'm going to show you an example why it makes a difference. There's a few differences in the complexity of the design and also in the behavior of the circuit, the timing of the circuit itself. So here's another really simple finite state machine. This one is an edge detector. Okay? Bits are received one at a time, one per cycle, such as this. All right? And we want to design a circuit that asserts the output for one cycle when the input stream changes from a 0 to 1. Okay, so it's detecting a change from a string of zeros to a string of ones. And when it sees the change, it's going to output. When we see a change from 0 to 1, we're going to output a 1 for one cycle. Okay, so we'll try this in two different solutions. I'm doing this to kind of demonstrate the difference between Moore and Mealy for you. Okay, so here's one solution. This would be a state transition diagram similar to what we've been drawing before for a Moore machine, because the outputs here are associated with the states. The way this one works is if we're in the 0 state and we get a 0, we stay in the 0 state, and the output is a 0. If we get a 1, then this is the change. So we go into this change state. So the circuit knows that it saw a change, and it asserts the output for 1. Now, if we get another 1, the signal's still high, but now we have to drop the output to a 0 because we said we want to assert the output for just a single clock cycle. So we get another 1, we go here. So we're in the 1 state now, and we change the output to a 0. So we have this state here just to distinguish between the inputs. We're still getting strings of 1s, let's say, but the output, it has to change. So we go to a different state for that. And if we get a 1, we just stay here. If we get a 0, we go back to the 0 state and start over again. If we had a 0 and we get a 1, we go to the change state, output a 1. If we get another 0 at this point, we go back to 0. So whenever we get a 0, we go back to the 0 state, right? Regardless of what state we're in. All right, so we need 3 states in the state machine to implement this function in this Moore-style FSM. And here is the state transition diagram where I've encoded 0, 0 for this state. The change state is 0, 1, and the 1 state is 1, 1. Again, I've just randomly picked bit patterns to represent these states. It may not be optimal, may not lead to the optimal circuits, but if you do that, and then I use 3 Carnot maps here, and based on the functions, the Carnot maps are filled in from the state transition diagram there, and I can write down these 3 functions, and with that, I can implement the circuit. Here's the 2 flip-flops that are used to represent the current state. So we have next state 0 leading into the bottom one, next state 1 leading into the top one, present state 0 comes out of the bottom one, present state 1 comes out of the top one. The output is this function. It's inversion of present state ANDed with present state 0. And then here's the next state logic. We take so next state 0 is just input, which is nice. Next state 1 is in ANDed with present state 0. So here's an AND gate. We take present state 0, AND it with in, and we get next state 1. Right, so this circuit, I claim, will do the correct function, which is this edge detector. Right? And you could kind of simulate this if you wanted to, or you could simulate it by hand or simulate it with a circuit simulator to verify that. OK, that was solution A. This is solution B. Now, if we allow ourselves to use a Mealy machine, things get simpler. It looks like this. If we have a 0 state and a 1 state. If we're in the 0 state, the input is a 0. It says we change the output to a 0 and then go back to the 0 state. If the input is a 1, we change the output to a 1 and go into the 1 state. If the input is a 1 here, we change the output to 0 and stay in this state. And then here, we get a 0. The output goes to 0 and the input, when the input is 0 here. And then we go back to the 0 state. Right? So we have 1 fewer states here because we don't have a special state. It's just hold the output as a 1 for 1 cycle. It happens, the output going to a 1 happens on this transition here. Right. So we can encode this as here I let 0. Now, since we only have 2 states, I need only 1 state bit. So we let the 0 state be represented by 0, the 1 state represented by 1. You can fill in this table. Here's the next state function here, and here's the output function. So the next state function is exactly in, and out is in ANDed with present state prime. So we get a circuit that looks like this, which is a lot simpler. So, but I'll show you in a minute. It has different timing behavior. So there's some intuition about the circuit, by the way. Remember, what we're doing is we're trying to detect an edge, right? So what this, you can kind of explain the circuit intuitively by, see, when you put a signal through a waveform, it delays the signal by 1 cycle. Right, so if that's the input, and our clock is, something like this, the output's going to come. So if this is next state, present state's going to look like that. It's a delayed version, delayed by 1 clock cycle. What you see here is that signal delayed by 1 clock cycle. Now, if you take these two signals and you invert present state, so you got this, and then we combine and this with this, you'll get this for the output. Right. So it's like take the signal, delay it, and then combine it with the delayed version of itself, or take the signal delay and add the and together, the delayed and then the non-delayed version. But you need an inversion in there to get it. But then you get that pulse out. Right. So if you were clever, perhaps if you saw the problem specification, you could have come up with this kind of circuit directly without having to go through the procedure. But it's good to know that there's a way to do it without, like I said, without thinking too much. All right, so we saw solution A and solution B. Solution A was the Moore machine. Solution B is the Mealy machine. What does this really mean? Well, look, I'll show you in a waveform. It's probably easiest to understand the difference between these two. Besides the fact that the Mealy is often simpler because it might have fewer states than the Moore machine, the Moore often has more states. It's a way to remember Moore versus Mealy. There's a timing difference in the way that the output is generated. So the output in the Mealy machine is, I will go back to this first before I show you. The output of the Mealy machine is some combination of the input and some state, but there's no register necessarily on this path. So if the input changes, the output will change instantaneously. On a Moore machine, the output only changes synchronously with the clock, after the clock edge, right? So we say that the output of the Mealy machine is asynchronous, and the output of the Moore machine is synchronous. And you can see this here. In these two solutions, here's the input changing. It changes, let's say it changes at this point in the cycle. We don't really know exactly where it changes, but what's important is on the Moore machine, we will transition into that state, what was it called? Got one state or the change state on this clock edge here, because we'll see this in along with the current state and change the state and the output at this point. So there'll be a little delay, but right after that clock edge, the output of the Moore machine will change. And it'll stay for one clock cycle, and it's guaranteed to go back down again if we put more ones in. The Mealy machine, though, because of the way we generate the output based directly on the input and the current state, as soon as the input changes, the output will change, right? Because it's on the edge. It doesn't have to wait till you actually get into the state. It doesn't have to wait for the rising edge of the clock. So the output will change to a 1 there, right? And that's fine. We get our specification is okay. We wanted a 1 for, we'll get it for not quite a whole clock cycle, right? It really depends on where the input change. If the input change was here, then it will go up here. If the input change is here, it's going to go up here, and we'll get it for a smaller amount of time, right? And then on the next rising edge of the clock, it's going to change to the here the will change to the other state, and the combination of that other state that along with the input will make the output go low. So that's really the difference. In solution A, both edges of the output follow the clock. On solution B, the output rises with the input rising edge and is asynchronous with respect to the clock. The output falls synchronously with the next clock edge. Right. So they're both useful, but you have to keep in mind that the Mealy machine has different timing characteristic. Okay, so here's kind of a comparison between the two. So solution A, the Moore machine, the output is a function only of the present state. In the Mealy machine, the output is a function of both the present state and the input. The Moore machine might have more states, right? You get a richer set of behaviors, a richer set of combinations if you can combine states and inputs to generate outputs. The Moore machine, you have to dedicate a state for each kind of unique output. Okay, so the more Mealy machine you might be able to have fewer states, which might mean simplified logic, right? Fewer flip-flops, simpler combinational logic circuits. The Moore machine has synchronous outputs. Right? If the input glitches, it's not sent to the output, right? Because the output only changes on the rising edge of the clock. Those glitches are ignored. If the input glitches on a Mealy machine, the output will glitch. The Moore machine kind of has this one cycle delay. The output doesn't actually reflect the change until the next clock cycle. The Mealy machine, the output changes immediately. That might be a useful thing for you. And then in the Moore machine here, in this example, we got a full cycle of stable output. In the Mealy machine, the output may not be stable long enough to be useful to you, right? Because if the input changes right before the clock edge, you're going to get just a narrow pulse there. The output will be 1 just for a short amount of time, because then when the clock edge comes, we're going to go to another state, and that's going to reset the output, right? So if you had the output of your finite state machine here, and it's going through some other combinational logic block, which is going to add some more delay, and then it goes into a register, right? Your whole thing might fail. Because, look, if the input changes here, the output of the Mealy machine is going to look like that. And then if you put it through some combinational logic block, it may push it over here, and then it won't be available for that clock edge. Right? So you could, of course, there's a way to fix this. Which is, if you really cared about this situation, before you went through a long delay like that, you could put it in a register here. And then that would hold it stable for a whole clock cycle. And then this register would have time, this circuit would have time to deal with it. And so that's essentially here. You can take a Mealy machine, put an output register on it, and then the timing behavior looks, at this point, out_R looks exactly like the timing behavior of a Moore machine. So the Moore machine kind of gives you registered outputs, which mean that they're stable for a whole clock cycle. They're easy to use on the next clock cycle. The Mealy machine, you could fix its output by putting a register there, but you effectively just have the same timing as the Moore. So you might as well have designed the Moore machine. Okay. Final note on this: a given state machine could have both Moore and Mealy outputs. There's nothing wrong with this. Right? But you need to be aware of the timing differences between the two types, right? And as I said, the timing behavior of the Moore machine can be achieved in a Mealy machine by registering the outputs. So if you didn't get the subtlety about the timing, you should think about it and study this. This is really kind of an important concept. If you understand this concept, you understand a lot about digital design and the timing of digital circuits, right? And the way that clocking guarantees correct behavior. Right? So, any questions about any of this? So, what I talked about today then was the basics of finite state machine design. What we're going to do next time on Thursday is to talk about how we optimize finite state machines. And there's two things to do to optimize them. One is to try to minimize the number of states. These examples were so simple that they're pretty minimal number of states, but oftentimes it's easier to design a state machine without worrying about how many states you have. And then you can find that some of the states are actually equivalent to one another. So we have techniques for finding equivalencies between states. If you have fewer states, then it takes fewer flip-flops and simpler logic in order to implement the state machine. It'd be cheaper and faster and lower power if we can do that. So that's one way to optimize it. The other way to optimize the state machine is by our choice of encodings for the states. Right? We have to have symbolic encoding of the states so we can keep track of which state we're in. How we choose that encoding, the actual patterns that we use can have an effect on the simplicity or the complexity of the logic functions for generating the output and for generating the next state. Right? So we'll talk about how to optimally choose state encodings as well. So that's coming up next time. And I think we are done for today. We are. So we're done 3 minutes early for a change. So we'll see you on Thursday.